It's okay. Oh no.
Too hard.
Oh no. Stop when we are ahead.
Alright, we've already done this. Right? If I give you a function, x squared minus 2x plus 7, how would we find the derivative? Remember, this is just notation for the derivative. dy dx is the derivative. So how would I find the derivative of this function?
Do the f of x plus h minus well, the limit.
Right, we're going to use the limit as h approaches 0 of f of x plus h minus f of x all over h. So let's take a minute and go through this here. Okay, so go ahead and find this derivative.
I might have just had a brain fart, but I think I fixed it.
Something better, Chance.
Are you okay?
No, I don't know why, but this class just makes me act silly. I heard that. Oh, it's okay. Well, we want it to get up to 100.
I don't know why. I don't know why we put a reward up there.
What do we get?
She said it, by the way.
And I don't even know why that's a reward either. I put my hair down.
Laughing. I have no idea what's going on.
Why can I keep up?
Wait, where did that?
So I guess I kind of skipped a step here. So once we get to this point where we're just left with 2x plus h minus 0, right now I am to a point where I can plug in 0 for h. So this is really 2x plus 0 minus 2. Good now? Alright. So any other questions on this process of finding a derivative? Alright, so now I'm going to show you how to do this in your head.
Well, that was
I know. Everybody is every year. Because the reason that we do this, okay, this is the definition of a derivative. This is how a derivative is defined. This is just slope, right? This is y2 minus y1 over x2 minus x1. Right? That's how we find the slope of a function. But there are shortcuts. So today we're going to look at the shortcut for any polynomial. Right? So I'll leave this function up here. Okay, we know we took the long way to figure out its derivative was 2x minus 2. Right? So our generic formula is this. If f of x equals a times x to the n, right? This is just a coefficient times x to some exponent, right? Just any term in a polynomial. Then the derivative of that piece, and we kind of already talked about this a little bit, right? We had an idea of what to do here. All I'm going to do is bring the exponent down. So it's going to be n times a times x, and then I subtract 1 from the exponent. Right. So for example, if I say that my function is 4x to the 5th power, then its derivative, I bring the exponent down, and I can multiply those together. Right? But I'll go ahead and I'll write it as this. So I bring my exponent down, so 5 times 4x, and then I subtract 1 from the exponent. Okay, so and then I can multiply those together to just get 20x to the 4th power. So the derivative of 4x to the 5th power is 20x to the 4th power. We just bring the exponent down and subtract 1 from the exponent. Okay. So if I give you, I don't know, 7x cubed, what's its derivative? 21x squared. Right? So we would have had to go through a pretty long process to find that before, right? Using the limit as h approaches 0 of f of x plus h minus f of x over h. Now we can do it in our head. Right? Yeah, so if I've got multiple terms, like this one up here, right? So let me erase these examples. What I can do is just take the derivative of each piece individually. Okay, whenever I'm adding or subtracting different pieces, I can take the derivative of each piece individually. So instead of thinking about taking the derivative of this whole thing, I can think about taking the derivative of each piece. So I can say the derivative of x squared minus the derivative of 2x plus the derivative of 7. Right? I can just take the derivative of each piece individually. So what would the derivative of x squared be? 2x. What would the derivative of, if I'm subtracting 2x, what would that be? What's the derivative of 2x? Okay. Yeah, so it would be negative 2. The way that we want to think about that is this is just a linear function, right? Negative 2x is a line. The slope at any point on that line is going to be negative 2. Right? We could also think about applying this rule. Right? If we think about this is negative 2x to the first, well, I would bring that 1 down. So 1 times negative 2 times x, and then if I subtract 1 from the exponent, that would be to the 0 power. And anything to the 0 power is 1, so I would just get 1 times negative 2 times 1, which is still negative 2. Now, how about the derivative of 7? So if we think, so what is this function? Right? If I just think about y equals 7, that's just a horizontal line, right? What's the slope of that line? 0. Right? So the derivative of any constant is 0. Right? So if we ever have a constant, its derivative is just 0. And we don't have to write that. Right? So using this shortcut, we just found that the derivative of this polynomial was 2x minus 2, which is what we found using the difference quotient earlier. Now we can do it in our head, though. So we can just, if we've got a polynomial like this, we can just take the derivative piece by piece. Okay?
This makes so much more sense to me than the other case.
Well, yeah, this is a shortcut. This is easier than using the definition of a derivative. Okay? So how about x minus x to the negative fourth power. If I throw in negative exponents. So yeah, so the rule is still going to apply, even if we have a negative exponent. So let's go piece by piece here. So 4x. What's the derivative of x? Will just be 1, right? If I think about my coefficient is 1, bring the exponent of 1 down. 1 times x to the 0 would just be 1. Now, if we apply the rule to this one, I've got minus x to the negative 4th. What's that going to look like? Exactly. And if I bring that negative 4 down, I'll have negative 1 times negative 4, which would be plus 4, and then subtract 1 from the exponent, I'll get negative 5. Good with that one? Yeah, it is. It's a shortcut. Alright, how about 2x to the 5th power plus 2 over x cubed. So the first one will be 10x to the 4th. What about this, though? 2 over x cubed. Is there a way that I can rewrite that? What is it? It would be. How did you? Actually, no, it wouldn't be. Sorry. You're close, though. So what was your thought process there?
Is it 5 over x?
So, as this is written right now, it does not look like terms we've been working with, right? It's not in the form of a times x to the n power. How can I rewrite this so that it is in that form? So if I've got an x cubed, how?
So over
You have to make the x's cancel out.
No. So if I've got an exponent in the denominator like this, that would be the same. So I'll rewrite this whole thing. That would be the same as bringing this up to the numerator as a negative exponent. So 2 over x cubed is the same as 2 times x to the negative 3rd power. Okay? 2 over x cubed would be the same as 2 times x to the negative 3rd power. So, whenever we see something like this, rewrite it as a negative exponent. Then we can apply this power rule. I guess I never actually gave a name to what we've been talking about. The rule that we're using is called the power rule. Whenever we see something like this, just rewrite it like this. So now, what's the derivative of this?
Negative 6 times.
X.
Negative 4. Alright, subtract 1 from the exponent. Alright, so now, on a standardized test, since our original function was written like this, generally you'll see the answer written like this. Okay, so I just want you to be comfortable going back and forth using negative exponents here. Alright. So let's try another one of those just to make sure that we've got that idea down here. So how about 7 over x to the 5th plus 2x minus 4 over x to the 4th. Okay, so first, before you take the derivative, rewrite it using negative exponents. Then take the derivative. Yeah, if you're thinking about going directly from here to here, yes. Except
Multiply
by the negative exponent, right? Yep. Yeah.
Like, will we ever see a situation where, for example, it would be like 7 over x to the 5th minus 3 or something like that? Should we have a binary number?
Yes, and in that case, we would not be able to use this rule.
Whenever we take next, do you want it in the bottom? Do you want us to do it in fraction form?
So if you are able to write out your answer, like if it's a free response type question, stop here. Right? However, on a multiple choice, you'll probably see it in this form. Right? On the AP test, they will accept any equivalent forms of answers. Right? So if you wrote it like this, they would take that. If you wrote it like this, they would take that. So always do the least amount of work. Right? If you get an answer, stop here. Right? Don't try to convert it. Because if you get this and then you mess up on this step, you'll mark it wrong. Right? Even if you had this correct, if you went a step further trying to simplify and messed up your simplification, it's wrong. Okay. Yeah. So once you get an answer,
Yeah.
stop there. Right?
Oh,
And,
okay, I know.
yeah, so good question. Anything else on this? Alright, so now let's use this same idea and take a look at something like this.
I have a phone.
It's not bad.
Oh, no.
How about something like this?
So we just so we want their
So yeah, the exponent would be 1/3. So we'll have 4/3 minus 1. So 4/3 minus 1 would be the same as 4/3 minus 3/3. So 4/3 minus 3/3 is 1/3.
And then 2 and 2/3 because 4/3 times 2.
Yeah, so 8/3 would be the same as 2 and 2/3, right? But improper fractions are a little easier to work with than mixed numbers.
Times negative 3 to the negative 1/2.
Right, times x to the negative 1/2. Exactly. Not too bad, right?
It wasn't bad. So I'm gonna try myself.
Approximately how far away is this test? Oh.
I think, yeah, the next chapter test.
Ooh, that's not good.
So the next big test will probably be a couple of weeks, but we'll have quizzes for that.
You didn't ask the right question. When's the next quiz?
I'm not sure yet. This is week 7, yeah.
Oh my god, me and you
How?
are gonna get this book. I know. We need to switch. Mine or my longer? I don't know. Yeah, when's that book due for fall? First. 2 weeks. Hey guys. That's crazy.
She's like,
Thank
Oh.
God. Thank God.
Oh.
I maybe it's just my friend cried yesterday.
Exactly. Alright, so let's take a look at something like this. Right? So in the last set of examples, we said whenever we've got a variable in the denominator, bring it up as a negative exponent to make it look like a times x to the n.
So we just make it
Exactly. Same idea here. If we have roots, we want to rewrite them as fractional exponents so that they're in the form of a times x to the n. So how can I rewrite the square root of x with a fractional exponent? Right. This would be x to the 1/2 power. How about the cubed root of x to the 5th?
5 to the 5th.
5 over 3.
Right. X to the 5/3 power. Oops, I wrote those in the wrong spot. Sorry, that's not the derivative. That's just rewriting this. Oops. Alright, so now let's take the derivative. So what would the derivative of x to the 1/2 be?
Negative x to the negative 1/2.
Right. Bring that exponent out. So 1/2 x to the negative 1/2 or x to the negative 1/2 over 2. Then the derivative of this one?
5 over 3x.
So now again, on a free response, stop there. That's your answer. But on a multiple choice, you would probably see it rewritten using roots, since our original function had roots in it. So how would I turn this back into a function with roots? How would I rewrite this now? So how can I make this exponent positive? Take it to the denominator. Right? Yeah, I mean, that's, so if I rewrote this as 1 over 2 times x to the 1/2, right? So then this is the same as the square root. So this, right, 1/2 x to the negative 1/2, I can rewrite as 1 over 2 square root of x, like that, if I want to turn it back into a root. How about this one? So this one isn't a negative exponent. So I don't have to take this one to the denominator.
The cubed root of
So 5/3 times cubed root of x squared. It does look a little ugly. But this, and I could even write it so it's all one fraction like that. So this would be the derivative of this function using our power rule. Okay? Questions? Alright, so when we're using the power rule, if we have variables in the denominator, bring them to the numerator with negative exponents. If we have roots, rewrite them as fractional exponents to make them look like a times x to the n, so we can use this power. All right. Questions? Great. Not yet. We've got one more thing. Then you can cry yourself to sleep. All right. So the last idea for today is finding horizontal tangents. Alright, finding horizontal tangents. So if we think about a graph, right, if I just draw some random graph, where on this graph are there going to be horizontal tangents? Exactly. And here at this max, I'll have a horizontal tangent, and also here at this min. So what is true about the derivative at those points? So what am I asking when I'm talking about the derivative? The derivative just means the what of this function? Slope. So what is true of the slope of the function at those 2 points?
0.
0. Right? The slope is equal to 0 wherever I have a horizontal tangent. So to find horizontal tangents of any function, what I want to do is find the derivative and then set the derivative equal to 0. So, for example, if I say find the horizontal tangents of 4x squared plus 7x minus 3. My goal is to find the places where the slope is 0, or where the derivative is equal to 0. So the first thing I need to do is find the derivative. What's my derivative here? 8x plus 7. So once I have the derivative, I want to find where it equals 0. So, yeah, I'm just going to get negative 7 over 8. So, if I were to graph this function, I would have a horizontal tangent wherever x is equal to negative 7/8. I mean, from what we've done so far, we haven't found y value where that would occur, but we know that at x equals negative 7/8, I'm going to have a horizontal tangent on my graph. You okay with one like that? Alright, let me have you do one more here. Think about how this one's going to work out. How about 1/3 x cubed minus 5/2 x squared plus 3x minus 4. I think that works out nicely. Oh, no, sorry. Make this a 6. Now that should work out nicely. 1/3 x cubed minus 5/2 x squared plus 6x minus 4. Yep.
We should get we should get an x squared part.
Yeah.
What am I doing?
You You should have 3 terms in your derivative.
We have to go back and get over here. That's what we do.
So now, yep. Alright, so did everybody get 3 and 2? Alright, so if we think about our original function, this was a cubic function. So it would look something like this, right? This general shape. We have 2 places where we have horizontal tangents. 2 places where the slope would equal 0. Alright, so power rule allows us to find derivatives of any polynomial. Bring the exponent down, multiply by the coefficient, subtract 1 from the exponent. If we see exponents in the denominator, break them to the numerator as a negative power. We see roots, turn them into fractional exponents. And if we want to find horizontal tangents, find the derivative, set it equal to 0. That was a lot today. All right. Any questions? Yes, you can